Swayam Prabha. Digital India. Educated India.
So now you tell me, you have broken down that reducible representation, right? A1G is accounted for, right? We have worked out the wave function for A1G, right? We have found what is A2U. Next we want to know what is E1G, what is E1U, what is E2G, what is E2U. How will I do it? For E1G and E1U, what should I combine? Right. So tell me then, what is psi E1GA? In terms of this size, psi 1 E1A, psi 2 E1A, psi 1 E1B, psi 2 E2B. So that's why I don't want to write so much. See, this is E1A, right? This combination. What is E1A? This one is plus, this one is minus, and so on and so forth. So that linear combination that you are trying to say, half of it is already worked out. Psi 1 E1A plus psi 2 E2A. What is that? Is it psi E1? Do you agree with that? Do you agree with that? Because in our convention, this is plus and this is minus, right? This is G, right? So, psi E1GA is equal to 1 by root 2 psi 1 E1A plus psi 2 E1A. What are we trying to generate? We are trying to generate the LCAO of the two rings together, right? When I try to do that, does it make sense to mix an ALCAO of this ring with, say, an E1A LCAO of the other ring? No, right? So A will mix with A, E1A will mix with E1A, E1B will mix with E1B, and so on and so forth. Right? Now what I am trying to tell you is this. This is your E1A. Right? Let us say this is a top ring. I denote the top ring by a subscript 1. So this is what? This is psi 1 E1A. Right? I denote the bottom ring by the subscript 2. That will also have a similar symmetry orbital of same symmetry. What will I call it? Psi 2 E1A. And it makes sense to mix them and generate an LCAO because they are the same symmetry. If I mix these, what symmetry will I get? If it is plus, then it is going to be ZA. Right? So E1 is already there, A is already there, it is going to become it is just that I have not left any space for G. That's why I stopped. Something like this. Right or wrong? If it is plus, then the p orbitals are both pointing inwards. Plus slopes inside or minus slopes inside, both of them. Right? So when you mix that kind of LCOs, what we were saying earlier also is that then you are bound to get something that is symmetric with respect to inversion. Right or wrong? So think of this, it's plus on this side, minus on this side. Okay, and then you take the same thing, put it out. Now you have to visualize, but then you have to turn it around also. So that plus is over plus, minus is over minus. Right? That is the meaning of plus. Okay, and since you are mixing E1A orbit, E1A kind of LCOs, the resultant linear combination is also going to have E1A kind of symmetry. The only additional thing that will come is that if it is a plus combination, then the subscript G will also have to come in. Right? Because by themselves, these rings do not have a center of inversion, do they? Does this ring have a center of inversion? No. Where does the center of inversion come from? Center of inversion comes from the fact that you have taken two such rings and you have placed them like this. Right? Now this and this, they are related by a center of inversion, isn't it? Now does it start making sense? You have this E1A linear combination of the top. You have another E1A linear combination at the bottom, sorry, like this. Okay, when you add them means this p orbital pointing inwards, this p orbital also pointing inwards. Plus slope pointing inwards, plus slope pointing inwards. That combination gives you the E1A symmetry with an additional symmetric behavior with respect to center of inversion. So that is why it is called psi E1GA. Make sense? So this is what the combinations are going to be. And now I have everything at a glance. So this we have all understood. Psi A1G is equal to 1 by root 2 psi 1A plus psi 2A. Psi A2U is 1 by root 2 psi 1A minus psi 2A. What is the psi 1A? The linear combination on the top ring whose symmetry is A. When I combine it with the same linear combination of the bottom ring, right, when the plus slopes point inwards, that is plus, then I get the linear combination that is symmetric with respect to inversion, and when it is like this, minus, then I get the linear combination that is antisymmetric with respect to inversion. Make sense? We are going back to what we had discussed a little earlier. Do you understand these two? If you understand these two, then let us look at this. 1 by root 2 psi 1 E1A plus psi 2 E1A. I am mixing the linear combinations of symmetry E1A of the top ring and the bottom ring. When I add them, once again I get a symmetric function with respect to inversion. I get a Jerede function. Make sense? Here when we added, it became Jerede. Here also when we add, it becomes Jerede. Rest of the symmetry remains the same. And when we subtract psi 1 E1A minus psi 2 E1A, you get psi E1UA. Because now this is what it is like, corresponding p orbitals, right? So let's see if you understand this. Have a look at these and tell me if you understand what is written there. What is there on the left hand side? On the left hand side, we have the SALCs of the two rings together. That is what we need when we want to talk about ferrocene. What do we have on the right hand side? What are these terms? Each term is an SALC of one of the rings. Okay? We might as well write this out completely in terms of 10p orbitals. Right? All we are trying to do is, since the 5-membered ring by itself is already a known system, we are trying to use the information that is available from the isolated rings, and using that we are trying to develop a description for ferrocene. So, on the left hand side you have the LCAOs of the two rings together. On the right hand side you have the LCO of the top ring separately and LCO of the bottom ring separately. So, the LCO of the two ring system is represented as linear combinations of LCAOs of similar symmetry of the isolated rings. Please read this and tell me if that makes sense, then we will proceed. So, this is E1G A, this is E1G B, right. So, what is A and what is B? When you work with the subgroup, then degeneracy is lifted, isn't it? And you have those complex numbers and all. We have done this earlier for this C3H3 plus kind of system. We worked with the full rotational subgroup and then we combined, we got back the same, we got back the entire picture. That is why you should combine them eventually. And you should work with the LCAOs that are there in the original group. It is just that since we have that A and B description, we are keeping the separation as far as possible. Finally, you have to combine. Now, so finally this is what we have to work with. We have generated more SLCs than we need. From there we can generate these. Now see, two candidates for combination with the A1G SLC. Okay. What about A2U? PZ? PZ is the only orbital, right? E1G? E1G you have DXZ and DYZ. We are looking for compatible orbitals. E1U? PXPY, right? And then E2G? Do I have a P x square minus y square orbital? D x square minus y square orbital? And dxy orbital? Right? We have it. What was that? E2G. What about E2U? Do you have anything of symmetry E2U? No. So that E2U SLC is useless, right? So knowing this, what you could do is, I don't know if you can read. Okay, I'll write. So these are the SLCs of the ring. You have A1G, A2U, E1G, E1, U, then this is E2G, E2U. Now tell me, in this D, what are the different symmetries that are there? A1G, E1G, E2G. What about S? This is A1G. What about P? Somebody said T. A2U, E1U. Okay. Now the problem becomes simple. What you have to do is you have to find the right match. But then don't forget that just match of symmetry is not enough. The energies must be close enough, otherwise they are not going to combine. Okay. So knowing the symmetries of the orbitals on the metal and knowing the symmetries of the LCOs, you can generate all these MOs of ferrocene, right? And you can see that some are going to be non-bonding because you are not going to have the right symmetry, or because the energy is not going to be very close. Okay. But once again, this is not a problem that can be solved only by symmetry. Computation is very much involved here. Okay. So that being there, A1G, E1G, E2G. What about S? This is A1G. What about P? Somebody said T. A2U, E1U. Okay. Now the problem becomes simple. What you have to do is you have to find the right match. But then don't forget that just match of symmetry is not enough. The energies must be close enough, otherwise they are not going to combine. Okay. So knowing the symmetries of the orbitals on the metal and knowing the symmetries of the LCOs, you can generate all these MOs of ferrocene, right? And you can see that some are going to be non-bonding because you are not going to have the right symmetry, or because the energy is not going to be very close. Okay. But once again, this is not a problem that can be solved only by symmetry. Computation is very much involved here.